Hello dear students, welcome to the lecture 13 of software engineering course. Today's topic is,
Dependability engineering.
the topics we are going to cover are in this lecture.
Redundancy and diversity. Fundamental approaches to achieve fault tolerance.
Fault tolerance is one of the most important things when you are developing a software or a system. Okay, we will see more about that.
Dependable processes. How the use of dependable processes leads to dependable systems. Dependable systems architectures. Architectural patterns for software fault tolerance. Dependable programming. Guidelines for programming to avoid errors.
One moment. Okay, I just verified that the microphone and video recording working. Okay, let's continue.
Software dependability. In general, software customers expect all software to be dependable. However, for non-critical applications, they may be willing to accept some system failures. Some applications, critical systems, have very high dependability requirements, and special software engineering techniques may be used to achieve this. Medical systems, telecommunications and power systems, aerospace systems.
You see, all these areas are extremely crucial systems. In medical systems, a system failure may result in death or serious injury of a patient. In telecommunications and power systems, they have to be online and working perfectly fine at all time because they are extremely important for our society to be continued. For aerospace systems, you can't even touch and fix if an error happens remotely. It's extremely hard to fix from remote, and you know how critical they are. However, let's say you are developing a game, it may be non-critical because if game crashes, you may lose your some game progress and nothing else in most cases.
Dependability achievement. Fault avoidance. The system is developed in such a way that human error is avoided and thus system faults are minimized. The development process is organized so that faults in the system are detected and repaired before delivery to the customer.
Okay, human error is avoided. You see, you follow some practices to minimize human error. Also, you add necessary checks to system so that the faults are detected and repaired before delivery to the customer. So you have teams to check and verify the software before you release it. Okay.
Fault detection. Verification and validation techniques are used to discover and remove faults in a system before it is deployed. Fault tolerance. The system is designed so that faults in the delivered software do not result in system failure.
Okay, so there are three main dependability achievements: fault avoidance, fault detection, and fault tolerance. Of course, what we want most is fault avoidance. We avoid fault, and if we can't avoid it somehow, we detect it, and if all fails, then the fault tolerance, which is our last defense, is being used. Okay.
The increasing costs of residual fault removal.
You see, there is some balance between fault removal and letting system to have some fault. Okay, so cost per error detected is you see like this. If you have very few number of residual errors, you have a lot of cost. Okay, why do you think it is this way? Because as you remove the common faults, the rare ones are harder to detect and remove. Therefore, the cost increases. Okay.
Regulated systems. Many critical systems are regulated systems, which means that their use must be approved by an external regulator before the systems go into service. Nuclear systems, air traffic control systems, medical devices.
Of course, these would have regulation from usually the government, because you can't just by yourself build a nuclear plant or build an air traffic control system or medical device. Okay, these are all in every country usually regulated systems.
A safety and dependability case has to be approved by the regulator. Therefore, critical systems development has to create the evidence to convince a regulator that the system is dependable, safe, and secure.
Okay, this is really important when you take a job of such software development or system development. They also provide you the set of rules that you have to follow and ensure that they are followed. Okay, you will. It is all about the regulations and the rules that has to be followed, or the things that has to be done.
Diversity and redundancy. Redundancy: keep more than one version of a critical component available so that if one fails, then a backup is available.
Okay, redundancy. For example, let's say your software system is extremely crucial. It has to be online all the time. If failure happens, it results in catastrophic damages. Therefore, then you keep clone of your live server, live software, and this is about being redundancy. For example, keeping your data in a RAID 1 array is having redundancy. Why? Because if one disk fails, you have clone of that disk in another disk. So it works, okay.
Diversity: provide the same functionality in different ways so that they will not fail in the same way.
You see, let's say you have a task that has to be completed, and you can use several different systems or software to do that task. So if you have diversity of components, if one fails, another one would work. Okay, this is about diversity, and this one is about redundancy.
However, adding diversity and redundancy adds complexity, and this can increase the chances of error. Some engineers advocate simplicity and extensive V&V as a more effective route to software dependability.
Okay, so what is extensive V and V? Okay. Let's see what is that. Okay, verification and validation. So some engineers are advocating that instead of taking the easy way, it is usually the easy way, increasing redundancy or diversity, they focus on making the software perfect as much as possible. So making the system fault free or error free. Okay, so this is another point of view, but from my perspective, I prefer redundancy, because redundancy is the easiest way and provides maximum security. As I have given example of RAID 1 array, if one of your disk fails, then you have another disk that is basically the clone of your failed hard drive. However, also this of course increases the cost of your system. Okay.
Diversity and redundancy examples. Redundancy: where availability is critical, e.g. in e-commerce systems, companies normally keep backup servers and switch to these automatically if failure occurs.
Okay, it is It is making sense.
Diversity. To provide resilience against external attacks, different servers may be implemented using different operating systems, e.g. Windows and Linux.
Okay, this is also making sense. Good examples. Let's continue.
Process diversity and redundancy. Process activities, such as validation, should not depend on a single approach, such as testing, to validate the system. Rather, multiple different process activities that complement each other and allow for cross-checking help to avoid process errors, which may lead to errors in the software.
Okay, you see, not just only depend a single approach to verify your software. You use multiple different processes, and each one of them complete each other and do cross-checking. So you may discover more errors and fix more faults and increase your dependency.
Dependable processes. To ensure a minimal number of software faults, it is important to have a well-defined, repeatable software process. A well-defined, repeatable process is one that does not depend entirely on individual skills, rather can be enacted by different people. Regulators use information about the process to check if good software engineering practice has been used. For fault detection, it is clear that the process activities should include significant effort devoted to verification and validation.
Okay, so it starts with our software process. It is about how we develop our software. If we follow the best practices, and rather than depending on individual skills, we depend on the teamwork and team check. It increases our software dependency. Also, for fault detection, we should have a dedicated team, dedicated effort for verification and validation. Okay.
Attributes of dependable processes.
Okay, process characteristic and description and documentable. So the characteristic of process is documentable. Let's see the description.
The process should have a defined process model that sets out the activities in the process and the documentation that is to be produced during these activities.
Okay, standardized.
Standardized.
Okay, standardized, whatever.
A comprehensive set of software development standards covering software production and documentation should be available.
Okay.
Auditable. The process should be understandable by people apart from process participants, who can check that process standards are being followed and make suggestions for process improvement.
Okay, diverse.
The process should include redundant and diverse verification and validation activities.
Okay, robust.
Robust. The process should be able to recover from failures of individual process activities.
Okay, let's see the validation activities. What are they?
Requirements reviews. Requirements management. Formal specification. System modeling design and code inspection. Static analysis. Test planning and management. Change management, discussed in Lecture 25, is also essential.
Okay, this is a lecture of next semester.
Fault tolerance. In critical situations, software systems must be fault tolerant. Fault tolerance is required where there are high availability requirements or where system failure costs are very high. Fault tolerance means that the system can continue in operation in spite of software failure. Even if the system has been proved to conform to its specification, it must also be fault tolerant as there may be specification errors or the validation may be incorrect.
So it may be impossible to produce a perfect system. Therefore, we need to have secondary plans, backup plans in case of errors, and even an unexpected error happens, our system should be fault tolerant enough to be continued. Okay, this is about being fault tolerant, this is about being dependable, so that even if it is a critical system, it wouldn't lead to catastrophic damages or health damage or such. Okay.
Dependable system architectures. Dependable systems architectures are used in situations where fault tolerance is essential. These architectures are generally all based on redundancy and diversity. Examples of situations where dependable architectures are used: flight control systems, where system failure could threaten the safety of passengers; reactor systems, where failure of a control system could lead to a chemical or nuclear emergency; telecommunication systems, where there is a need for 24/7 availability.
One moment. Okay. So, of course, in flight control system, system failure could threaten safety of passengers because aircrafts may crash, collapse. In reactor system, of course, a nuclear blast may happen. And in telecommunication systems, rather than errors, they have to be online every time because, let's say, you had an accident and you have to reach to the emergency service, the hospital, you call them for ambulance and system is not available, then you would have a health hazard and such.
Protection systems. A specialized system that is associated with some other control system, which can take emergency action if a failure occurs. System to stop a train if it passes a red light; system to shut down a reactor if temperature, pressure are too high.
You see, these are protection systems rather than prevention.
Protection systems independently monitor the controlled system and the environment. If a problem is detected, it issues commands to take emergency action to shut down the system and avoid a catastrophe. Protection system architecture.
Okay, so we have a system environment and then we have external system. The protection systems are external systems, so error in the system environment doesn't prevent them from working. Protection sensors, which let's say monitors the system environment, and then we have protection system. Then we have actuators such as shut down the system or lower the temperature or whatever. Controlled equipment, and there is control system and sensors. It is working like this basically.
Protection system functionality. Protection systems are redundant because they include monitoring and control capabilities that replicate those in the control software. Protection systems should be diverse and use different technology from the control software. They are simpler than the control system, so more effort can be expended in validation and dependability assurance. Aim is to ensure that there is a low probability of failure on demand for the protection system. Self-monitoring architectures. Multi-channel architectures, where the system monitors its own operations and takes action if inconsistencies are detected. The same computation is carried out on each channel and the results are compared. If the results are identical and are produced at the same time, then it is assumed that the system is operating correctly. If the results are different, then a failure is assumed and a failure exception is raised.
Okay, you see the same computation. This can be such as reading temperature from multiple, let's say, multiple sensors at the same environment, and if they are different, that means that one of the sensor or the system is incorrectly working. Okay, it is something like that. So the same computation is carried out on each channel. Okay, on different channels.
Self-monitoring architecture.
Okay, we have input value, and then we have splitter, channel 1, channel 2. So we compare them with a calculation, and if they are different, then it means that there is some error in the system.
Self-monitoring systems. Hardware in each channel has to be diverse so that common mode hardware failure will not lead to each channel producing the same results. Software in each channel must also be diverse, otherwise the same software error would affect each channel. If high availability is required, you may use several self-checking systems in parallel. This is the approach used in the Airbus family of aircraft for their flight control systems.
Okay, you see, if high availability is required, you may use several self-checking systems in parallel. So let's say you have 5 systems checking at the same time in parallel, and 2 of them gets broken. You see how hard it is for all of them to be fail at the same time to cause an error. This is about being dependency and high availability. Why? Because if aircraft system collapses, okay, then aircraft may crash, and which may lead to the death of all passengers. You see how catastrophic result it is. So based on which software you are working, you have to think about every possibility, okay, and take necessary actions. This is totally dependent on your software, on the software type.
Airbus flight control system architecture.
Okay. In Airbus flight control system architecture, let's check it. So we have input channels. You see there is primary flight control system 1, which even splits to check in itself to verify whether it is working or not with multiple channels inside. And if they are not same, that means that then there is an error. Then they have primary flight control system 2, primary flight control system 3. Okay, so these are primary flight control systems. Then they have secondary flight control system 1. It is exactly same as the primary flight control system, and then they have secondary flight control system 2 and 3. So if primary flight control system fails due to an error or something, then the secondary system takes control. This is a redundant system, and it is exactly clone as the first system. So both of them has to fail to have problem. Maybe they have primary flight maybe they have flight control system 3 as well. I don't know how many they have, but as you increase the number of redundant systems that can take over control when one fails, you increase your chances to be dependent. Okay. What I mean is it is extremely hard and unlikely for all of your systems to fail at the same flight. Okay. So this is the basic idea. Okay, so there is the key sentence here. Let me show you. Okay, for example, this one is a key sentence.
If high availability is required, you may use several self-checking systems in parallel.
And not only that, but okay, there was another sentence, but where was it? Okay, here, this one.
These architectures are generally all based on redundancy and diversity.
So if you want to have a fully dependable system, then you have to use redundancy and diversity. Okay, no other easy or cheaper way. For example, this is the redundant system. and it also has diversity with in control here, different channels. Okay, let's continue.
Airbus architecture discussion. The Airbus FCS has 5 separate computers, any one of which can run the control software.
Okay, you see it has 5, not 2, not 3, not 4, 5. So all of them has to fail at the same flight for aircraft to be unusable. Okay, and it is extremely highly unlikely scenario.
Extensive use has been made of diversity. Primary systems use a different processor from the secondary systems. Primary and secondary systems use chipsets from different manufacturers. Software in secondary systems is less complex than in primary system, provides only critical functionality. Software in each channel is developed in different programming languages by different teams. Different programming languages used in primary and secondary systems.
You see, they not only cloned or added a redundant system, they also made sure that they are using diversity. Even different processors, different programming languages, different system software. Why? Because a bug may exist in the system 1 and that bug may not have been discovered yet. And let's assume that you are using all clone of the first system. So the clones will also have that bug in that particular occasion. Okay, let's say if the weather is minus 30 degree, your software has a bug and your first system failed. So then the second system gets into the control, but that system is also clone of your first system. Therefore, it also has that bug, and that secondary system also crashes immediately because the environment didn't change, and your third system takes control, but it also has that bug because it is also clone of the first system. So you see how diversity may have a significant role in your dependability. Okay, so the key points of the part 1.
Dependability in a program can be achieved by avoiding the introduction of faults, by detecting and removing faults before system deployment, and by including fault tolerance facilities. The use of redundancy and diversity in hardware, software processes and software systems is essential for the development of dependable systems. The use of a well-defined, repeatable process is essential if faults in a system are to be minimized. Dependable system architectures are system architectures that are designed for fault tolerance. Architectural styles that support fault tolerance include protection systems, self-monitoring architectures, and N-version programming.
You see, N-version programming is using different programming versions. Okay, let's repeat again.
Dependability in a program can be achieved by avoiding the introduction of faults, by detecting and removing faults before system deployment, and by including fault tolerance facilities. The use of redundancy and diversity in hardware, software processes and software systems is essential for the development of dependable systems. The use of a well-defined, repeatable process is essential if faults in a system are to be minimized. Dependable system architectures are system architectures that are designed for fault tolerance. Architectural styles that support fault tolerance include protection systems, self-monitoring architectures, and N-version programming.
Okay, let's continue dependability engineering part 2, N-version programming.
N-version programming. Multiple versions of a software system carry out computations at the same time. There should be an odd number of computers involved, typically 3. The results are compared using a voting system and the majority result is taken to be the correct result. Approach derived from the notion of triple modular redundancy, as used in hardware systems.
So this was about N-version programming.
Hardware fault tolerance depends on triple modular redundancy, TMR. There are three replicated identical components that receive the same input and whose outputs are compared. If one output is different, it is ignored and component failure is assumed. Based on most faults resulting from component failures rather than design faults and a low probability of simultaneous component failure.
Okay, so if you use inversion programming and hardware fault tolerance, you increases your chance of dependability extremely high. Okay, because it is very unlikely for multiple hardware to fail at the same time, in addition with multiple software to fail. This is about triple modular redundancy. You see we have input A1, A2, A3 and output, and based on the most voting we can count it as the correct one. This is for hardware, and we have inversion. It is also same.
N-version programming. The different system versions are designed and implemented by different teams. It is assumed that there is a low probability that they will make the same mistakes. The algorithms used should but may not be different. There is some empirical evidence that teams commonly misinterpret specifications in the same way and chose the same algorithms in their systems.
So it is not the developer teams do not have to use different algorithms. However, if they use same algorithms, then they may make the same mistake at the same time independently. Okay.
Software diversity. Approaches to software fault tolerance depend on software diversity, where it is assumed that different implementations of the same software specification will fail in different ways. It is assumed that implementations are A, independent and B, do not include common errors. Strategies to achieve diversity: different programming languages, different design methods and tools, explicit specification of different algorithms.
Okay, so you see, if you use different programming language, if one programming language has a bug, and using different one may prevent it. Different design and methods and tools, which prevents different teams to make same mistake, same logic mistake perhaps. And explicit specification of different algorithms means that basically different algorithms, therefore it is very highly unlikely to make same mistake in the different algorithm.
Problems with design diversity. Teams are not culturally diverse, so they tend to tackle problems in the same way. Characteristic errors: different teams make the same mistakes. Some parts of an implementation are more difficult than others, so all teams tend to make mistakes in the same place. Specification errors: if there is an error in the specification, then this is reflected in all implementations. This can be addressed to some extent by using multiple specification representations.
So you see, in big software development, always there are specifications, and developers follow those specifications. So if the specification itself is incorrect, then all teams will make that mistake naturally. And to fix that, there could be multiple specification representations, but it was solving the software, it was solving the problem at some extent, as you can see.
Specification dependency. Both approaches to software redundancy are susceptible to specification errors. If the specification is incorrect, the system could fail. This is also a problem with hardware, but software specifications are usually more complex than hardware specifications and harder to validate. This has been addressed in some cases by developing separate software specifications from the same user specification.
Okay.
Improvements in practice. In principle, if diversity and independence can be achieved, multi-version programming leads to very significant improvements in reliability and availability. In practice, observed improvements are much less significant, but the approach seems leads to reliability improvements of between 5 and 9 times. The key question is whether or not such improvements are worth the considerable extra development costs for multi-version programming.
Okay, so it is of course will improve your reliability no matter what. However, does it worth to the extra cost or not? This is the key question. So in aircraft technology, it may, because there is no way or there is no luxury to have failures. Okay, or in aircraft, aerospace design, or in nuclear plant design and such. So it is totally up to your system and its fault having luxury. Okay, so you have to keep the balance.
Dependable programming. Good programming practices can be adopted that help reduce the incidence of program faults. These programming practices support fault avoidance, fault detection, fault tolerance.
Okay, of course, following good programming practices will reduce your uh, error events and failures. It is, of course, best to follow good practice guidelines always.
Good practice guidelines for dependable programming. Dependable programming guidelines. 1. Limit the visibility of information in a program.
What does this mean? This means that use the appropriate access modifiers. So if a variable has to be, it should be private, make it private. If it should be protected, make it protected. Or if it has to be public, then make it public. Okay.
2. Check all inputs for validity.
This is always number one rule. Never trust the input from coming from external resources that you cannot control, that you do not control.
3. Provide a handler for all exceptions.
This is also true. Never leave an exception unhandled and have global handlings as well.
4. Minimize the use of error-prone constructs.
Let's see. If your construct, your struct is open to make errors, make mistakes, then you should not use it. Okay, you should reprogram it and remodel it. So minimize the use of error-prone constructs.
5. Provide restart capabilities.
This is true. So if system stucks for any reason, you should be able to restart it. Recently, I read an article and they restarted the system with, let's say, some very crucial limited timing. Okay. Okay, I'm trying to find the article. Okay, let's say. Okay. Okay, I can't find it, but it was something about the system stocks in the aircraft, and it has to be restarted and then take the necessary maneuver from to prevent burning from the sun. Okay, I can't remember the correct keywords. Let's continue. Check array bounds. Why? Because if you do not check the array bounds, then you would get index error or array size error, and it would lead to crash of your application. Include timeout when calling external components. Why? Because you do not have in control of external components, and they may never provide you the response, or they may not provide you the response in valid time period. Therefore, you have to have timeout to prevent application from waiting forever the external input. Okay. Name all constants that represent real world values. This is also really important because naming makes your software much more interpretable. What I mean is, other developers may read your software and understand your objects means what, represent what. Okay, so it would lead improved checking and verifying your software from multiple teams, multiple developers, or external regulators and such. Okay.
Control the visibility of information in a program. Program components should only be allowed access to data that they need for their implementation. This means that accidental corruption of parts of the program state by these components is impossible. You can control visibility by using abstract data types where the data representation is private and you only allow access to the data through predefined operations such as get and put.
Okay. In C#, for example, this is get and set. Very famous.
Check all inputs for validity. All programs take inputs from their environment and make assumptions about these inputs. However, program specifications rarely define what to do if an input is not consistent with these assumptions. Consequently, many programs behave unpredictably when presented with unusual inputs, and, sometimes, these are threats to the security of the system. Consequently, you should always check inputs before processing against the assumptions made about these inputs.
Never trust your input. Never ever. This is number one rule, unless it is coming from the system you are controlling. Okay.
Validity checks. Range checks. Check that the input falls within a known range.
Size checks.
Check that the input does not exceed some maximum size, e.g., 40 characters for a name.
Representation checks.
Check that the input does not include characters that should not be part of its representation, e.g., names do not include numerals.
And reasonableness check.
Reasonableness checks. Use information about the input to check if it is reasonable rather than an extreme value.
Okay.
Provide a handler for all exceptions. A program exception is an error or some unexpected event such as a power failure. Exception handling constructs allow for such events to be handled without the need for continual status checking to detect exceptions. Using normal control constructs to detect exceptions needs many additional statements to be added to the program. This adds a significant overhead and is potentially error-prone.
Okay, let's see the architecture of exception handling. Okay, there is code section, normal flow of control, exception detected, normal exit. And to be able to normal exit when exception happens, we have to have an exception processing code in somewhere else. You see, this is exception handling code. Okay, exception handling, and let's read it.
3 possible exception handling strategies signal to a calling component that an exception has occurred and provide information about the type of exception. Carry out some alternative processing to the processing where the exception occurred. This is only possible where the exception handler has enough information to recover from the problem that has arisen. Pass control to a runtime support system to handle the exception. Exception handling is a mechanism to provide some fault tolerance.
For example, if you are developing a, let's say, web crawler and you have a main crawler engine, so you can follow this approach. Let's say you keep 10 concurrent crawlings at the same time. However, and you start a new one when one of them finishes its task. So if they fail for any unreason, any unseen reason, unhandled reason, then it would never get completed. So your crawler may stuck with waiting your crawling tasks to be completed, and therefore you can add an exception that would handle if the crawling task is ended with an exception, with an unhandled exception. So you can you can add them in the C#, for example, continue with exception, and so that would attach to your task, and if your task ends with an exception, with an unhandled exception, then your exception handling would be called and it would exit normally. Okay, like displayed here, normal exit.
Minimize the use of error-prone constructs. Program faults are usually a consequence of human error because programmers lose track of the relationships between the different parts of the system. This is exacerbated by error-prone constructs in programming languages that are inherently complex or that don't check for mistakes when they could do so. Therefore, when programming, you should try to avoid or at least minimize the use of these error-prone constructs. Error-prone constructs. Unconditional branch goto statements floating point numbers inherently imprecise. The imprecision may lead to invalid comparisons. Pointers referring to the wrong memory areas can corrupt data. Aliasing can make programs difficult to understand and change. Dynamic memory allocation runtime allocation can cause memory overflow.
Okay, this floating point numbers is an issue, really issue. For example, depending on the programming language you are using, let's say you keep 3.0 in the memory. However, it may be kept as 2999999, something like this. Okay, or you are keeping, let's say, something like this. However, it may be kept as something like this. So this is a real issue, inherently imprecise. And if you compare these numbers, of course, they wouldn't be same.
Error-prone constructs. Parallelism can result in subtle timing errors because of unforeseen interaction between parallel processes. Recursion errors in recursion can cause memory overflow as the program stack fills up. Interrupts can cause a critical operation to be terminated and make a program difficult to understand. Inheritance code is not localized. This can result in unexpected behavior when changes are made and problems of understanding the code.
Okay, so in parallelism, you have to have a very well defined synchronization between parallel processes. If they are not in sync, then you will have a lot of problems. Recursion is a self-calling function, and they can easily fill up your stack, because each time when a function called itself, then it adds to the stack heap of the program, And if you do not start returning from the functions at some point, your memory may fill, your heap or function called heap may fill, and you will get overflow, which I had in the past. Interrupts can cause critical operation to be terminated because ongoing operation would be interrupted. In inheritance, if the inherited class is written, for example, some other developer, and if they change the way it works, then your class inheriting that parent class may get broken as well. Okay.
Error-prone constructs. Aliasing using more than one name to refer to the same state variable. Unbounded arrays buffer overflow failures can occur if no bound checking on arrays. Default input processing an input action that occurs irrespective of the input. This can cause problems if the default action is to transfer control elsewhere in the program. An incorrect or deliberately malicious input can then trigger a program failure.
Of course, every time when you are getting an input from user, think user as a malicious intent having user. Think as you are getting input from an hacker, and always write your code with this consideration. Even if you are setting a code to a private company, every time always consider that the hackers will work at that company and will try to crash your software or do malicious things. Okay, so this is number one rule. Always check the input, always sanitize the input.
Provide restart capabilities. For systems that involve long transactions or user interactions, you should always provide a restart capability that allows the system to restart after failure without users having to redo everything that they have done. Restart depends on the type of system. Keep copies of forms so that users don't have to fill them in again if there is a problem. Save state periodically and restart from the saved state.
So this is same as let's say draft. You see, when you are typing an email, it automatically saves draft of that email. So even if your computer crashes, your browser crashes, or some other reason you left it, then you can continue writing your email from that draft. So in here, what restart means, that restart actually resume from wherever you left with restarting the system as well. Okay.
Check array bounds. In some programming languages, such as C, it is possible to address a memory location outside of the range allowed for in an array declaration. This leads to the well-known bounded buffer vulnerability, where attackers write executable code into memory by deliberately writing beyond the top element in an array. If your language does not include bound checking, you should therefore always check that an array access is within the bounds of the array.
Okay.
Include timeouts when calling external components. In a distributed system, failure of a remote computer can be silent so that programs expecting a service from that computer may never receive that service or any indication that there has been a failure. To avoid this, you should always include timeouts on all calls to external components. After a defined time period has elapsed without a response, your system should then assume failure and take whatever actions are required to recover from this.
Okay, as I said, never trust the behavior of external components. Never ever.
Name all constants that represent real-world values. Always give constants that reflect real-world values, such as tax rates, names rather than using their numeric values, and always refer to them by name. You are less likely to make mistakes and type the wrong value when you are using a name rather than a value. This means that when these constants change, for sure, they are not really constant, then you only have to make the change in one place in your program.
Okay, this is an error that I have encountered in the first year programmers. They are writing the constant value everywhere needed in their program. This is extremely wrong, because let's say you had to change that number, then you have to find that number everywhere in your software and make changes. Therefore, always define constants, define values for settings as settings, and refer to those fields and properties in C#, for example. They are called like that. So that even if you change the number or the value of that constant, then you don't make the change anywhere else. Okay, this is really important. Never hard code numbers in your application. Use constant, name it constants. Okay, whatever the programming language you are using. So the key points of the chapter 2.
Software diversity is difficult to achieve because it is practically impossible to ensure that each version of the software is truly independent. Dependable programming relies on the inclusion of redundancy in a program to check the validity of inputs and the values of program variables. Some programming constructs and techniques, such as goto statements, pointers, recursion, inheritance, and floating point numbers, are inherently error-prone. You should try to avoid these constructs when developing dependable systems.
Okay, let's repeat.
Software diversity is difficult to achieve because it is practically impossible to ensure that each version of the software is truly independent. Dependable programming relies on the inclusion of redundancy in a program to check the validity of inputs and the values of program variables. Some programming constructs and techniques, such as goto statements, pointers, recursion, inheritance, and floating point numbers, are inherently error-prone. You should try to avoid these constructs when developing dependable systems.
Yes, it is not advised to use any goto statements, and when using pointers, actually I would suggest you to not use any programming language that still uses pointers, such as C, C++. I, for example, use C#, Java, or Python. And if not possible, of course, we may use C or C++. Recursion, do not use it unless it is explicitly necessary, because they increases your program complexity, makes it harder to understand. Inheritance, however, is commonly used in object-oriented programming. However, it also has some drawbacks if different programs or teams are programming the inherited parent class or child class. And floating point numbers, always be very careful when you are making comparison or other things, because they are not very precise. I mean, after a certain point of degree, their precision differs. And this is it. So the end of lecture 13, and hopefully see you next week. I will now upload our this week lecture slides. Okay, hopefully see you next week, and end of lecture.